Hello and welcome to this video on finding the standard matrix for a given transformation. And this is, I've done a video on this in the past, if you've been following along with me, where I found the standard matrix for a transformation, a linear transformation, right? Because linear transformations are matrix transformations. But these were for transformations between Euclidean vector spaces, right? So from R2 to R3, R4 to R, right? Just the sets of vectors with so many components that were real numbers. Well, today, in this video, I'm going to talk about finding the standard matrix for a linear transformation between any two vector spaces. All right? And the key to this is going to be taking a transformation between any two vector spaces and transforming it, representing it in some other way that involves the coordinate vectors of vectors from the domain and codomain. Alright, so again, you might want to go back and brush up on coordinate vectors or finding the coordinates of a vector relative to a specific basis that I put up a video on before, or find it somewhere else if you can. So let's begin. Alright, so matrix transformations. So let T from, say, vector space, it'll be a transformation from vector space V into W. Alright, be a linear transformation between vector spaces V and W. Suppose that set B is the standard basis for vector space V. Alright, so B is a standard basis for V, meaning every vector in V can be written as a linear combination of these, and these vectors are linearly independent. Also, they're the simplest of building blocks for V. That's why they're the standard basis. Okay. And suppose set C is the standard basis for vector space W, right? Because again, these might not be the same vector space. Right. And if you know a basis for each of these, then you know their dimension. Alright, for the vector spaces. So suppose that the dimension of V is n. Right, so there are n vectors in the standard basis for V. And the dimension of W, say, is m, meaning that there would be m vectors in the standard basis C for W. Right, and notice how this is really everything I do from this video is, and as I've done with most videos here, is working with finite dimensional vector spaces. Alright, then we can represent T as a transformation assigning the coordinates of a vector in V relative to basis B to the coordinates of a vector in W relative to basis C. Alright, so we can take a transformation between any two vector spaces and represent it in a different way, represent it in a way that we have a transformation between coordinates relative to basis B from V into coordinates relative to basis C from W, right, of W. So it would look like this. Right, it would look something like this, and I've got examples coming up at the end of the video where I'm doing this. Right, so if this isn't making sense right now, hopefully it will later. So this is saying, like, alright, so if I'm given a vector, say x from the domain, right, from V, right, so we have this linear transformation T from V to W. So x is from the domain. We can write a rule. If it's a linear transformation, we can write a rule like this, where I apply, again, it's a representation of T. It's not exactly T, right? But it's T of, and then my input is a vector, right? The coordinate vector of x relative to basis B. So I find the coordinates of x relative to basis B. That's what this notation meant. Right? I plug this into a transformation, a new representation of T, and the output is another coordinate vector, right? So my input is a vector, my output is a vector, and this is the output is the coordinate vector of t of x, right? What the normal output would be in w, right? Relative to basis c. All right, so what I have written here is called the coordinate vector, well, I'm calling it the coordinate vector representation of t. All right, like I said, if all the fancy notation and whatnot, if this isn't making sense, hopefully it will when I start going through examples. And what you're going to notice here is, my input is a vector, my output is some vector with so many components, where each component is a coordinate of a vector relative to a certain basis. Right, so it'll be just like I took a vector with n components, right? Because there would be n coordinates, right? The dimension of v was n. Basis b had n vectors in it. I would be taking a vector with n components and getting an output with m components. Remember I said earlier, say the dimension of w was m, or basis c, right, would have m vectors in it. So any vector from w, when you wrote its coordinate representation, its coordinate vector would have m components. So this representation of t will be as though t is a transformation from Rn to Rm. It'll be just like this, even though it's not, right? We're just going to take a general linear transformation and, again, represent it as one that's between Euclidean spaces, all right? All right, so you'll see in a minute here when I get through some examples. Now, since t is a linear transformation, it is then also a matrix transformation. I talked about this before as well. Again, I hope you've been following along videos of mine, matrix transformations, and how a matrix transformation is a linear transformation and vice versa. Now, being a matrix transformation, that means we can express t in the following way. We could express the output here, right, this coordinate vector of t of x relative to basis c of w. We can represent this output as a matrix times the original input vector, right, that input coordinate vector. So we can express t in the following way, right, where, again, t of, and then my input is just the coordinates of my input vector with respect to basis b, should be able to be written then as a matrix A multiplied by that same input vector, right, the coordinates of x relative to b. And this matrix A here, where it would be an m by n matrix, is called the standard matrix for t. All right, and then some more fancy jargon that, again, hopefully will make some sense when I actually get through some examples. If you want to make A quickly, the columns of A are the coordinate vectors of the images of the coordinate vectors of the standard basis vectors relative to B, relative to C. All right, and notice I tried to make this as clear as possible by doing some underlining with different colors here. So the columns of A, the columns of this standard matrix, are the coordinate vectors of the images relative to C, right? They're both in underlined in green and parentheses in green. So the images of these red guys, what I underlined in red, the coordinate vectors of the standard basis vectors relative to the standard basis, right? The images of these, I write the coordinates of those relative to C, and those give me the columns of A. Again, lots of fancy jargon. Maybe not very clear here with all the words and fancy notation around. All right. Hopefully this will all be clear after some examples. All right, so that's what the rest of the video is on. So for the rest of the video, now this isn't the only thing I'm going to be doing, but I'm asked to find the standard matrix for the linear transformation T. All right, so I am told already, and you can check if you want, you can check that that additivity property and homogeneity property hold to show that this transformation is linear. but I'm given examples here where we already know that T is a linear transformation, and we're asked to find the standard matrix for this transformation. All right, so here T is a transformation between this. Remember this P2. This is the set of all polynomials of degree 2 or less. And again, under standard operations, right? If I don't specify operations, just assume it's standard. The normal way you add polynomials, the normal way you're multiplying polynomials by scalars. And it's from P2 to P3, where again this is the set of all polynomials of degree 3 or less. And the rule here, T takes an input from P2. All right, so T of P of x here, this is some polynomial degree 2 or less, and it's equal to x times P of x. All right, so for example, some examples of outputs here. T of x. Right, this is a polynomial of degree 2 or less. This is from P2. Would be equal to x times x, or x squared. Right, and this is a polynomial from P3. T of x squared minus 3x plus 1 would be equal to x cubed minus 3x squared plus x. Right, just multiplying the input P of x, the input polynomial, by x. Right, so and you would be distributing the x. That's why I got this here, multiplying every term by x. So yeah, so I could do this all day long, right? Fine. Take all sorts of inputs, take any polynomial of degree 2 or less, plug it into this, and get a polynomial that's degree 3 or less. Great. All right, so the question is, how can I write this? How can I express this as a as a matrix transformation between coordinates relative to a standard basis for P2 into coordinates for relative to a standard basis for P3? Okay. So what are the standard bases for P2 and P3? Now this has come up in a previous video. I'm just going to write it down here. So the standard basis for P2. Again, I'm going to call this B, right? The like in an earlier page, the standard basis for the domain. Well, every polynomial of degree 2 or less can be written as a linear combination of a constant, right? 1, just an x, and an x squared. Right? Every polynomial of degree 2 or less is a linear combination of these three: some number times 1 plus some number times x plus some number times x squared. And they are linearly independent. Right? And you can test all that out on your own. And so the dimension, right? We've seen this before too, right? The dimension of P2 is 3, right? There are 3 vectors in here. Okay, that's the standard basis of the domain. And then let me do the same thing for the codomain, P3. Standard basis for P3 is, again, I'm going to call this C like I did in the earlier pages, right? And this is made up of the vectors 1, x, x squared, and x cubed, right? Because every polynomial of degree 3 or less can be written as a linear combination of these 4, right? Some number times 1 plus some number times x plus some number times x squared plus some number times x cubed. And these are also linearly independent. You can't write one as a linear combination of the others. So we're seeing here that the dimension of P3 is 4. Right? There are 4 vectors in this standard basis. All right, so what I'm going to do next is, right now I have a transformation between 2 vector spaces that are not Euclidean, right? These are not R2 and R3 or R4 and R5 or something. But what we are going to see is, what I'm going to do is I'm going to write that coordinate vector representation for t, where we can kind of represent this transformation as something that's like going from R3 to R4, right? This has dimension 3, this has dimension 4. So you're going to see me write this map, write this transformation as a representative of the transformation that looks like it's from R3 to R4. Right, so I'll start this on the next page. So here we're going to start making our coordinate vector representation of t. All right, so if you take a look at a general input, right, what does an input look like? And I'll keep the standard basis for the domain up here. So if I have an input vector, right? So an input vector, say again x, that belongs to P2, right? Something from the domain. What is that going to look like? Well, every vector x is going to look like this. You know, what does every polynomial of degree 2 or less look like? Well, you have some constant term, I'll call it a0, plus some linear term, say a1 times x, plus some quadratic term, a2 times x squared, right? This is what every vector in P2 looks like this, right? Where a0, a1, and a2 are, say, real numbers, right? Didn't really specify, but let's say real numbers, right? Now, if you think about this, now remember the coordinates. The coordinates of a vector relative to a basis are the coefficient. When you write what are the weights of the linear combination, right? This is a0 times 1 technically, plus a1 times x plus a2 times x squared. So these coefficients, right, you see these are the basis vectors, 1, x, and x squared. These coefficients, right, the a0, the a1, and a2, these are the coordinates or the weights of x relative to basis b. Coordinates of x relative to basis b. All right, so instead of plugging this in, what we're going to do is represent the input by its coordinate vector. All right, so the coordinate vector of x relative to basis b looks like a vector from R3. All right, where again I just put the coordinates, I put the weights of the linear combination the linear combination of these three basis vectors that make x. I put them in the same order that the basis vectors come in, so that what's the coefficient of 1 first, then x squared. So the coordinate vector of x relative to basis b, that's going to be a0 here, right, the coefficient of 1, then a1, the coefficient of x, and then a2, the coefficient of x squared. All right, so this is going to be my input when I change this to its coordinate vector representation. Right. Okay. And then the output, all right, the output. Remember, the output is, what is t of x? What is the value of the transformation or the image of x under this transformation? And this would belong to the codomain, right? P3. Well, let's go through and remember x looks like this. What is t of x? Now if I go through this, just x, remember t applied to a polynomial from P2 is just x times that polynomial. So I'd multiply this by x. So I'd have a0, times x plus a1 times x squared plus a2 times x cubed. Right? And remember that standard basis for P3. Right? There's the standard basis for P3. It's made up of these four vectors. So what I'm going to do now is, I wrote the coordinates of the input relative to basis B. I'm going to now write the coordinates of the output relative to basis C, right? The basis for the codomain, the output set. Let's see. Let me write this as a linear combination of these four. Well, you see how there's no constant term. So there's 0 times 1. And then plus, and then you have the rest of it, some a0 times x plus a1 times the vector x squared plus a2 times the vector x cubed. And just as before, right, these coefficients, right, the coefficients 0, a0, a1, a2 are the coefficients of these four basis vectors. Those are the coordinates of the output relative to this basis, relative to basis C. All right, I'll point that out again. So again, the 0, the a0, the a1, the a2, these are the coordinates or the weights of that linear combination. The coordinates of t of x, right, this vector is called t of x, right, relative to basis C, or relative to C. All right, and so the coordinate vector of t of x relative to C, I'm going to write it as a vector. So this coordinate vector for t of x relative to basis C is, now again, just the coefficients in the order that I wrote the standard basis in. All right, notice I wrote the standard basis in that order. So the and this will be just like something from R4, right? Some vector with four components, where the first one, the coefficient of 1 is 0. Then the coefficient of x is a0. Coefficients of x squared is a1. Coefficient of x cubed is a2. All right. Okay, and then now I can write what's called the coordinate vector representation of t. All right, so this was our original rule for t, and now I'm going to write it this way, where we have coordinate vectors. All right. So let me write this out again. So now here it is, the coordinate vector representation for t. So here, t of, and I'll write the way it was in that last page. What my input is going to be the coordinates of the original input vector with respect to the basis B, right? They're the basis of the standard basis of the domain, and the output, right, is going to be the coordinate vector of what the original output would be with respect to basis C, the standard basis for the codomain. So popping these in, right, I had here is my coordinate vector for any input, right, the coordinate vector for any input with respect to basis B. So we're getting this rule here, t of vector a0, a1, a2 would be equal to, and then the coordinate vector of the output with respect to basis C would be, and I showed you here, this one here, 0, a0, a1, a2. And do you see now how it's just like, again, this is, I should write the B here and the C here, just so you know that these are coordinates, right? because the vectors themselves, right? Remember, the vectors themselves in this transformation are polynomials. They're not, vectors that you're used to from R3 or R4. So I will put these, the little basis B, basis C on the bottom here, just to let you know that these are coordinates, not the actual vectors themselves, right? These are representing the actual vectors, but not they aren't the actual vectors themselves. But do you see now how this is like, again, this is now like a transformation from R3 to R4? It really is, right? Because I'm taking a coordinate vector with 3 components and mapping it to a coordinate vector with 4 components. Now it becomes just like a video I put up in the past. Again, I hope you've watched it. If not, don't worry about it. I'm going to do it again here. Now I can put, since we're told this is a linear transformation, so I should be able to write this output as a matrix times this input vector. All right. And I said it would be an m by n, 4 by 3. All right, so that's going to be a 4 by 3 matrix, where down each column, right, down each column are just going to be the coefficients of my input variables. So my input variables in this coordinate vector here, my input coordinates are a0, a1, a2. So down the first column, I'll put the coefficients of a0 in my output. There's no a0 in the first component, 1 a0, no a0, and no a0 again. And then down the column, the second column, I put the coefficients of my second input variable, a1. There's no a1 in the first component, no a1 in the second component, 1 a1 in the third component, and then no a1 in the fourth component. And then down the third column, I put the coefficients of my third input variable in the output here. Right? There's no a2, no a2, 0, no a2, and then 1 a2. And there's this 4 by 3 matrix that I said would happen. This is going to be the standard matrix for this transformation, and this is multiplied by the input vector, a0, a1, a2. Again, I'll just make sure I'll put a little b down here just so you know that these are coordinates. But think of matrix multiplication. If I multiply this 4 by 3 times this 3 by 1, there's a 3 by 1 vector here, I would get this back, wouldn't I? And you can double check it. All right. And then here we go. All right. This is the standard matrix. This is the standard matrix for T. Okay, so now let's see let's use this. All right, let's use this. If I go back to the very first page for this example, let's see if this is actually working out, right? Because if this works, if this standard matrix statement I made down here is correct, then all these statements I wrote up here should also be, every input and output I had on the when I was doing these examples here in the beginning, where t of x was x squared here, t of x squared minus 3x plus 1 was x cubed minus 3x squared plus x. These should also be true in this coordinate representation, the coordinate vector representation. All right, so let's see that working out. So I'll go back here. All right, so let's say recall from earlier that t of x was just x squared in this rule, right? T of x was x squared. Now if I translate this to the coordinate vectors stuff, right? If I look at just the coordinate vectors, if I say use coordinate vectors, what's the coordinate vector of just x with respect to basis b? Well, basis B was just that basis for the standard basis for P2. That was that 1x x squared. So this is, 0 times 1 plus 1 times x plus 0 times x squared. Right. And what's the coordinate vector for x squared, right? The output with respect to basis C, right? The output is with respect to the standard basis for the codomain. The codomain, right, that was P3. That had standard basis 1x x squared and x cubed. So if I write this as a coordinate vector, and again, just so you know, these are coordinates, right? 0 times 1 plus 0 times x plus 1 times x squared plus 0 times x cubed, right? So it'd be this 4 by 1 vector. Again, these are coordinates with respect to basis C. Well, let's test this out. Test our standard matrix statement out up here. Right? So if I'm saying, can you find t of x? If I say use coordinate vectors to find t of x, right, now I know it's x squared, but let's say we find t of x. Well, if I go to the coordinates, right, and use this standard matrix, we should be seeing that t of, the coordinates of x, which are 0, 1, 0, right, again with respect to b, but I'll just write 0, 1, 0. I plug the coordinates of x in with respect to b. According to what I wrote up here, this should be equivalent to this 4 by 3 matrix, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, multiplied by my coordinates, the coordinates of x, the coordinates of the input. And let's see what we get. Now I'm hoping, right, again, these are coordinates with respect to b. I should be getting an output that are, coordinates with respect to basis C. This better be this 0, 0, 1, 0. Right? Well, look, it's a 4 by 3, right, times a 3 by 1. So it'll be a 4 by 1, like I want. The first row is all zeros, so this is 0 for the first row, first column. Then you have 1, 0, 0 with the 0, 1, 0. Do that little matrix product there. That's 0 plus 0 plus 0. That's 0 again for the first row, second column. Then 0, 1, 0, 0, 1, 0 for the third row, first column. 0 plus 1 plus 0, that's 1. And then 0, 0, 1 with 0, 1, 0, 0 plus 0 plus 0. And look, and again, these should be coordinates with respect to matrix C. All right. So that means that t of x, right, so t of, and again, what these coordinates here represent x, equals, and then these coordinates represent x squared, right? 0 times 1 plus 0 times x plus 1 times x squared plus 0 times x cubed. And there we go, right? We're seeing the same thing I saw up there. All right. Let's do another one. All right, another one from earlier was this, t of x squared minus 3x plus 1. All right, now I'll come back to this. What's t of x squared minus 3x plus 1? And using the same standard matrix. All right, so let's find t of x squared minus 3x plus 1 in this rule. Now again, I know it's going to be x cubed minus 3x squared plus x because you're simply multiplying the polynomial by x. But let's use the coordinates. Right? So I change it to its coordinates relative to b. Relative to basis b. So t of, and then the coordinates of this vector relative to b was, you have 1 time, remember my first vector in the basis was 1, so I'm looking at the constant term first, so 1 times 1 plus negative 3 times x, and then plus 1 times x squared, right? I'm doing it in the order that I put the vectors in the standard basis. Right? If the vectors were in the other order, I'd write it in the other order. Now again, this is coordinates with respect to b here. Now, according to what I wrote a minute ago, right, this should be equal to that standard matrix, right? The standard matrix was that 4 by 3 matrix. And I'll write it here again. Here was the standard matrix for this particular transformation. should be this multiplied by my input, 1, -3, 1. And I'll get an output that's a 4 by 1. It's a 4 by 3 times a 3 by 1 again. And these should be, now the output should be coordinates with respect to C. All right. Now if I multiply these, zeros for the, so 0 here, then 1, then -3 if you do third row with this column, and then 1 when you do the fourth row with this column. And there we go. Right? And then what do these correspond to? Right? So t of, remember what these coordinates here correspond to the vector x squared minus 3x plus 1 is equal to, and then these output coordinates correspond to the vector 0 times 1 plus 1 times x minus 3 times x squared plus 1 times x cubed. All right, and remember that's what I got earlier, right? If you multiply this polynomial by x, you'd get x cubed, right? X cubed minus 3x squared plus 1 times x plus 1 times x. It works out, and that's exactly what I got earlier. Right? Just the other order. Right? All I did was I wrote the terms in the other order. Okay, so hopefully this makes sense. How we're just taking our input vectors and like writing it as the, as coordinates with respect to the standard basis for the domain, and taking our output vectors and writing those as coordinate vectors with respect to the standard basis for the codomain. All right, now that other statement I made, right, still related to this example. There was one last statement I made that might have been a bit confusing, and I'll show you what this means here. This last statement I made earlier, the columns of A, right, the columns of the standard matrix are the coordinate vectors of the images of the coordinate vectors of the standard basis vectors relative to B, relative to C. Yeah, right, very wordy. Let me show you in this example. All right, so this transformation, going back to the beginning, back to the same example. The standard basis for the domain, right? Again, B was this 1x squared. What I'm going to do is I'm going to find the images of these and write the coordinates of those images relative to basis C. All right. So going back to this page, I'm going to take the standard basis B and I'm going to find its images under T. All right, so what's T of 1? Well, T of 1 would be just x times 1, or x. Now again, I'm going to translate this to coordinates. All right, what are the coordinates relative to C? Right, so over here, I'm going to have the coordinates, let's put chords, relative to C, right, rel to C. Right, sorry if that's too cluttered, too close there. So x, now the basis C here for P3, there's, this is 1x, so it's 0 times 1, right? 0 times 1 plus, 1 times x, and then there's no x squared, there's no x cubed. Right, there's the coordinates of that vector relative to C. And look at this and compare it to the standard matrix. Right, here is the standard matrix on the last example I did. Look at that. See that? 0, 1, 0, 0. And look at the first column of the standard matrix. Here it is here, right? The standard matrix is this guy here. 0, 1, 0, 0. Hey, same thing. So if you'd like to also, another way to make this standard matrix for a transformation is just take your standard basis vectors, plug them in, and then translate them to, write them as their coordinates relative to the basis for the codomain. All right. Let's do another one. Right, that was T of 1. Right, T of 1, that basis vector. What's T of x? Well, according to this rule, T of x would be x times x, or x squared. And again, let's change x squared to its coordinates relative to basis C. and that would be, there's no constants, so 0 times 1, there's no x term, so 0 times x. There's an x squared term, it's 1 times x squared, so 1x squared. And then there's no x cubed terms, so 0, 0, 1, 0. 0, 0, 1, 0. And now look at the second column, right? This was the second vector. We're going in order here. Look at the second column of the standard matrix, right? 0, 0, 1, 0, 0, 0, 1, 0. Hey, they're the same. All right, and then one more time here. Plug in the third basis vector, x squared from b. T of x squared is x cubed. And again, we'll translate this, we'll change it to its coordinates relative to basis c. And there's no constants, so 0 times 1. There's no x's, 0 times x. There's no x squareds in this. And there's 1x cubed. So 0, 0, 0, 1. And look at the last column, the third column of my standard matrix here, right? 0, 0, 0, 1, 0, 0, 0, 1, the same. So that's what I meant on the bottom of one of that a couple pages ago, where I said the columns, right? The columns of the standard matrix of the transformation are just the images, right? The images of the basis vectors from B, but translated to coordinates relative to C. Right. Okay, so that's a lot. It's a lot there. Let's try it with another example. I've got a few. All right, so this time, again, I'm told, all right, and you can verify this yourself, this is a linear transformation. It satisfies the additivity property and the homogeneity property. Right? So here, T is a transformation from the set of 2 by 3 matrices with real entries to the set of 3 by 2 matrices with real entries. And T of A is a 2 by 3 matrix. Right. My input is a 2 by 3 matrix with real entries, and then the output, is A transpose, right? Remember when you transpose, the rows and columns switch. So the output, A transpose, that is a 3 by 2, right? It belongs to R 3 by 2. That's the 3 by 2 matrix output. Okay. Now what I'm going to do here, just as before, is I'm going to write the standard bases, right? The standard bases for these spaces. So the standard basis for R, the set of 2 by 3 matrices, and I'll call this B. Now remember, for this m by n matrices, the standard basis just contained all the m by n matrices where exactly one entry was 1 and the rest were 0. Made the simplest building block. So I'm going to start in the upper left hand corner entry. That's 1, and it's a 2 by 3, right? So there's a 2 by 3 where one entry is 1 and the others are 0. And then we're move the next one over, right? And so that matrix, this matrix, 0, 1, 0, 0, 0, 0. This matrix 0, 0, 1, 0, 0, 0. And I'm just moving the 1 around, right, to all the positions. 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 1, 0, and finally 0, 0, 0, 0, 0, 1. Right, this was the standard basis for the set of 2 by 3 matrices. Every 2 by 3 matrix can be written as a linear combination of these 6 matrices, right? So we're seeing that the dimension of our domain is 6, right? There are 6 vectors, 6 matrices in this standard basis. And if you recall from an earlier video, right, the dimension of the set of m by n matrices was simply m times n, right? How many positions are in the matrix, how many entries. All right, and then the dimension, and then a standard basis the standard basis for the codomain, the 3x2 matrices, is similar, right? But they're just all 3x2 matrices. For our 3x2, again, I'm calling this C, right, for codomain or whatever. And again, this is just a set of all 3x2 matrices where the exactly one entry is a 1 and the rest are 0, and I'm just going to move the 1 around the different positions. So the first one in the upper left-hand corner, and then 0 everywhere else, right? So there's a 3x2, and then 0 here, 1 there. Just moving the 1 around, 0 everywhere else, and 0, 0, 1, 0, 0, 0, and then 0, 0, 0, 1, 0, 0, 0, 0, 0, 0, 1, 0, hey. And then finally, 0, 0, 0, 0, 0, 1. Alright, so there's a basis, the standard basis for R 3x2. Every 3x2 matrix can be written as a linear combination of these 6, and these 6 are linearly independent. You can't write one as a linear combination of the others. And so we're also seeing that the dimension of R 3x2 is also 6. Alright, so what I'm going to do now is I'm going to find that standard. This time I'm going to do the other way around. I'm going to find the standard matrix first and then write the rule in its coordinate vector representation. I'm going to write T in its coordinate vector representation using the standard matrix. Okay. So let's go through. Right, there's the standard basis vectors. Now, hopefully you remember, all this rule does is take a matrix and send it to its transpose. Right? So vectors from B, right? Images, we're looking at the images of the vectors, the matrices from the standard basis for the domain. Right? We're looking at those. So what's T of, you know what, I'm going to call these so I don't have to keep writing all these matrices. Let's call this B1, B2, B3, a little vector notation above them, B4, vector B5, and vector B6. All right, let's just call those. So and I'm going to go in that order. All right, so what's the value of T at vector B1? All right, well, that would be the transpose of this matrix here, which is going to be this 3x2. All right, so the first row is now the first column, right? 1, 0, 0. And the second row is the second column, right? So it's this 3x2. Now, as I said, this doesn't give me a column of the standard matrix. What will give me a column of the standard matrix is now I'm going to translate this into its coordinates. What are the coordinates of this matrix relative to the matrix, relative to the standard basis for the codomain? So what are its coordinates? Right, chords relative to C, right, relative to this standard basis. All right, so now it's dimension 6, right? The codomain is dimension 6, so these are going to be like 6 by 1, like 6 component vectors here. And you see how this matrix is just one of this first one. Obviously, it's the same thing. And then none of the others. Right? 1 of this plus 0 of that, 0 of that, 0 of that, 0 of that. So 1, 0, 0, 0, 0, 0. Right? Like I said, there should be 6 components. Right? 1 of this and 0 of the other 5. 1 and then 5 zeros. And again, this is relative to C here. Those are the coordinates of this output. The coordinates of this image relative to basis C. All right, then T of B2. All right, B2. And here's B2, this matrix. All right, so again, the first row becomes the first, it's the transpose, right? The first row becomes the first column. So 0, 1, 0, 0, 1, 0, and then zeros, 0, 0, 0. All right, and I translate this to coordinates relative to basis C. Well, let's bring basis C back. So it's none of this, 1 of that, right? Because that is the matrix. So 0, 0, 1, 0, 0, 0, right? It's this and none of the other things that make this matrix. So again, a nice 6-component vector. All right, oh yeah, I forgot to mention, right? This is going to be the first column of the standard matrix. Right. Then this will be the second column. So again, none of these first two, 1 of the third one, so 2 zeros, then a 1, then 3 zeros. Right. Again, it'll be 6 components, right? That's dimension 6. And this will be the second column of my standard matrix. Right. All right, then T of B3, and I'm going to go through all 6 of these, all right? So bear with me. T of B3. Now B3 is this, just the transpose of this. So the first row, 0, 0, 1, is the first column of the output, right? So 0, 0, 1, and then there's zeros again. All right, and then I translate this to its coordinates with respect to basis C. I'll look at basis C again. So this matrix here is this one. So I have none of this, none of this, none of this, none of this, 1 of that, and none of this. So 4 zeros, a 1, and a 0 for my components in the coordinate vector. So 4 zeros, a 1, and then a 0. All right, and again, this is relative to basis C. And this will be the third column of my standard matrix. All right, then T of B4. Okay, T of B4. The fourth basis vector from B, the fourth basis vector, standard basis vector of the domain. B4 is this. I'm doing the transpose, right? So first row is all zeros, so first column's all zeros. Then 1, 0, 0, 1, 0, 0. All right, again, translate this to its coordinates relative to basis C. And here is basis C again. So you see how this is none of this, 1 of that, right? It's that matrix right there. It's the second one. So 1 of the first one, 0 of the first one, 1 of the second one, and then 0 of the other four. So when I write it as a column vector or coordinate vector, it's 0 of the first one, 1 of the second one, and then 0 of the other 4. And there's again relative to basis C, and then this is the fourth column of our standard matrix. T of B5, right, the fifth standard basis vector in B. And just the transpose of this matrix. So again, the first row, column is all zeros because the first row was all zeros. Then 0, 1, 0. And then again, now we'll write the coordinates of this relative to basis C. Now this matrix here is this fourth matrix, right? 1, 2, 3, 4. So 0, 0, 0, 1, 0, 0 for the coordinates relative to C. 0, 0, 0, 1, 0, 0. All right, and this will be our fifth column of the standard matrix. And then finally, for the standard matrix, the last column, T of B6. Right, so I apply, do the transpose of B6, this matrix here. With so 0 for the first row, that'll be zeros for the first column. And then we had 0, 0, 1, so 0, 0, 1. And then translate this again to coordinates relative to basis C. Here's basis C. This matrix is that last one. All right, so it's none of the first 5, and then one for one of the sixth ones. So 5 zeros, and then a 1. All right, and this will be the sixth column of the standard matrix. All right, so now that I've got, I mean, it's a lot, right? There were 6 of these, but so now that I have every column, we can write the coordinate vector representation of T. I'll do that here. All right, so here is the coordinate vector representation of T. Yeah. So remember, T of some matrix A was equal to, A transpose, right? T of A was A transpose normally. All right, so what we're going to translate that to, or we're going to change this to, is T of, the coordinates. I'll say the coordinates of vector of matrix A, or vector X, or whatever, right? Whatever you want to call the input, A or X. If I plug in the coordinates of A with respect to basis B, right, the standard basis of the domain, I'll get this standard matrix, which is going to be a 6 by 6. Right? And again, just going back here, and I'm copying them the way I had them. All right. So the first column was that that output of the first standard basis vector translated to coordinates relative to C. So it was 1 and then 5 zeros. All right, and then the second column was 2 zeros, then a 1 and 3 zeros. Third column was 4 zeros, a 1 and a 0. The fourth column, 0, 1, and then 4 zeros. Fifth column, 3 zeros, a 1 and 2 zeros. And then the last column, 5 zeros and a 1. So I should be able to take this is the standard matrix, this 6 by 6, right? 6 by 6. This is the standard matrix for T. I should be able to get the output here and multiply this matrix by whatever my input was, right? My input, the coordinates of A with respect to B, right? And this should give me the transpose, right? And if I take, this will give me coordinates in C, right? This will give me a vector that's a coordinate vector in C, right? This whole side, whenever I find that product, this will give me a coordinate vector relative to C, relative to that standard basis for the codomain. And then I translate that back, and you'll see that it's actually equal to the transpose. All right, so let me test this out. All right, let me test this out. Now, I'm going to, just because I don't want to keep writing it over and over again, I am going to enter this matrix, because I don't want to, again, I don't feel like writing it a bunch. I'm going to enter this matrix into my calculator, so bear with me here. And in fact, you know what, I'm just going to pause the recording right now while I do this. Okay, so I've entered this 6 by 6 matrix, this standard matrix here. All right, that's matrix A on my calculator. And I'll get out of here and we'll come back to this. Let me get out, go to quit. Back to the main screen. Come on. All right, I don't. Something's delaying on this. Let me get back to the main screen. Sorry. Okay, got back to the main screen. So now what I'm going to do is I'm going to test this out. All right, when I test this out, let's now this is an easy transformation to plug and play with, right? But let's say I wanted to find what's T of, and remember A is a 2 by 3 matrix, right? We're going from R 2 by 3 to R 3 by 2. All right, this was the transformation here. Right. And the output's just the transpose. So let's find R, and then I'll plug in, any 2 by 3 I wish. I'll just do simply 1, 2, 3, 4, 5, 6. Right? There's a 2 by 3 matrix. Now, again, we know that the output should be the transpose of this, right? So the 3 by 2, where the first column is 1, 2, 3, and the second column is 4, 5, 6. But let's actually plug in. Now again, I'm going to call this standard matrix just S for standard matrix, right? So this should be equal. Well, we'll figure out what it's equal to in a second. What I'm going to do is I'm going to translate the input to coordinates. Right, now the input's coming from the R 2 by 3. So I'm going to translate it to its coordinates relative to basis B, right, relative to the basis for the domain. So this would be T of, and basis B was all those 2 by 3 matrices with the ones in one position and zeros everywhere else. So I'd have one of that first so if I change this to coordinates, right, I'd have one of that first matrix, 2 of that second matrix, 3 of that third matrix, 4 of the fourth, 5 of the fifth, and 6 of the sixth, right? So again, this thing with 6 components in here, this is basis B here, right, relative to basis B. This should be equal to, all right, this should be equal to the when I plug in this, it'll give me something that's equal to our standard matrix S, again, this 6 by 6 behemoth up here, multiplied by this coordinate vector, 1, 2, 3, 4, 5, 6. Right. And this will give me a new coordinate vector. Right? Let's see what that is. All right, so I'm going to go back here, back to the matrix menu. And I'm going to enter a new matrix. I'll call it B. I'll go down to B here. And this is a 6 by 1. I'm going to enter this 6 by 1 column vector. All right, so 6 by 1. All right, and the entries are 1, 2, 3, 4. Oh, it messed up on me. All right, sorry, I'm going to finish this. Okay, so I've got this 1, 2, 3, 4, 5, 6, this column vector entered. And then I'm just going to multiply these, right? That giant 6 by 6 standard matrix times this here. And we'll go matrix. All right, sorry, I'm going to pause this again. This is really slow on me today. All right, so now I see I have A. This A here is that behemoth, right? And then the B is that's the 6 by 6 standard matrix, and B is the 1 to 6 column vector, the coordinate vector for our matrix, our input. And look what we get when we enter this. This is 1, 4, 2, 5, 3, 6. All right. We get 1, 4, 2, 5, 3, 6. And this is with respect to C there. All right. So let's translate this back into, remember this is with respect to C, standard basis C. That was the standard basis for those 3 by 2 matrices. So this is, now remember what basis C looked like one more time. So this means it's, 1 of this matrix plus 4 of the second plus 2 of the third plus 5 of the fourth plus 3 of the fifth plus 6 of the sixth. So the first row will be 1, 4. The second row will be 2, 5. The third row will be 3, 6. So I get a 3 by matrix 1, 4, 2, 5, 3, 6. And look at that. Isn't that the transpose of this matrix, right? This is indeed the transpose, which we were hoping for. Yay, right? But this will work for any matrix, right? I'm not going to do any more here because it seems the calculator is getting slow on me today, this little calculator app. But yeah, if I put any matrix in here, if I changed it to its coordinates relative to B, then multiplied those coordinates by this giant standard matrix, I'll get the coordinates relative to C, and then I can translate back and give me the output, right, if you'd like. Now I know this was an easy one to just say, hey, just take the transpose. You know how to transpose. I'm just saying, if it's a linear transformation like this is, you still can do it this way as well, right? Find a standard matrix and write the coordinate vector representation of the transformation, and use the standard matrix and coordinates of your vectors to get outputs that are coordinate vectors as well, and then translate back. All right, so I got one more here. Long video today. Sorry, they're always long. Who am I kidding? All right. So here again, I have a transformation that is linear. Right? It is linear, and you can check that for yourself. Right? So check the additivity property and the homogeneity property. Here, my inputs are polynomials of degree 2 or less, and my output is some real number. All right. So remember, this is dimension 3. This is dimension 1. And let me put the standard bases. All right, and the rule works like this. Take T, I plug in this, again, my input is some polynomial of degree 2 or less, and the output is, the definite integral for you calculus people, right? The definite integral from 0 to 1 of that polynomial, right? Which again, you do a definite integral over some specified interval, you will get a real number back. All right, so for the domain, right, what's the standard basis for P2? Now we've seen that, right? Standard basis for P2. That's this 1x squared, or you could write it as x squared x and 1, or whatever order you want. But whatever order you write it, make sure you stick to that order. All right, be consistent. All right, so I'm going to do it the same order I did earlier. So remember, every polynomial of degree 2 or less is a linear combination of these three, and these three are linearly independent. So the dimension of P2, as we've seen earlier, is 3. All right, and a standard basis for the real numbers is just the number 1. Right? Every real number is some scalar multiple of 1. Right? Some real number is just that real number times 1. So standard basis. Oh yeah, and I called this B, didn't I? Right? I should call this B, right? The standard basis for the domain for P2. Then the standard basis for the reals, right, is just the set with the number 1, just the number 1. Right? And I'll call this C. So the dimension of the reals is 1, right? 1 vector 1. All right. So now I'm going to go about finding that standard matrix. Now, remember, this is dimension 3 here, this is dimension 1, so the standard matrix is going to be a 1 by 3 matrix. You'll see. All right. So let's find that standard matrix. So that's where I take the standard basis for the domain set, and we find their images, right? And then write their coordinates, with respect to the standard basis for the codomain. But since the standard basis for the codomain is only the number 1, this is going to be pretty simple. All right, so what's T of the first standard basis vector from the domain. That's what's t of 1. Well, that'd be the integral from 0 to 1 of just 1 dx. Well, that would just be, remember, an antiderivative of 1, and it is x. And I plug in 1, plug in 0, subtract, I get just 1, right? And then 1 is the coordinates, right? When you talk about translating this to the coordinates, it would just be 1 with respect to c. 1 times 1 is 1. Simple as that, right? So this this column here with the number 1, that's going to be the first column. The first column of the standard matrix. All right, then the next standard basis vector from B is x. What's t of x? Integral from 0 to 1 of x dx. Now again, this is half x squared. Plug in 1, plug in 0, subtract, just plug in 1. That's a half. And again, if I were to write this as its coordinates, with respect to basis c, this is just a half times 1, so it's a half. All right, so there's the second column. I'm just going to write second column of the standard matrix, and then finally the t of x squared. Sorry, that should be x squared. Scratch that up. T of x squared, right? The third basis vector from B. This is the integral from 0 to 1 of x squared dx. All right, and this is 1/3 x cubed. Plug in, it's just a third. Plug in 1, plug in 0, and subtract. So coordinates here, just 1/3. This is 1/3 times 1, right? With respect to the basis c, just the number 1. So the coordinates are simply 1/3, right? And there's the third column. All right. So the standard matrix again is a 1/3, where these are the 3 columns. All right. So let me write this on the next page. We can now take transformation t here, right? T of p of x, right? T is some polynomial, right? Is the integral from 0 to 1 of that polynomial, with respect to x. But let's translate it to its coordinates, right? Let's write let's do again the coordinate representation. I'm just going to say chord rep this time, right? Remember the coordinate vector representation of t. So this is where I take t, I plug in the coordinates of the polynomial with respect to basis b, right? With respect to that basis with 1x and x squared in it. And it should be equal to the standard matrix. All right, now the standard matrix is going to be a 1/3 with these 3 columns: 1, 1/2, 1/3. 1, 1/2, 1/3. 1, 1/2, 1/3. There's your standard matrix, a 1/3 matrix. And then this would be multiplied by that input vector, right? the coordinates of the polynomial with respect to basis b. And then this output, right? When you take this product, right? When you take this product, again, this product of these two will give you a coordinate vector with respect to basis c. Right, with respect to c, or relative to c. Right? That's with respect to WRT, coordinate vector with respect to c. All right. Okay, so let's test this out. So using what we know here, can we find the value of t at, say, 2 minus 4 plus 4x plus 5x squared? All right, 2 minus 4 plus 5x squared. Now you could do it with the rule, right? I can just plug this in for p of x and then take the integral. It shouldn't be that difficult. But I'm trying to show you how we can use the coordinates and standard matrices to help us find this as well. So instead, what I'm going to do is change this to its coordinates relative to b. All right, now remember, b was 1x x squared, right? Basis b for p2 was 1x x squared, in that order. So when I write the coordinates, I'm going to write the coordinates in that order. The coefficient of 1, coefficient of x squared. Okay, so we'll have t here, t of, and then the coordinates of this relative to b are, you have 2 times 1, negative 4 times x, and then positive 5 times x squared, right? This is relative to b here. Okay. Now, according to what I've written here, this should be equivalent to our standard matrix, 1, 1/2, 1/3, multiplied by this input vector with 2, negative 4, and 5 as components. And what are we getting? Well, we have a 1 by 3 times a 3 by 1. This is a 1 by 1, a single number. And this will be with respect to c then. Right, the output should be coordinates with respect to basis c. Let's see. You do 1 times 2, 2 plus half times negative 4. So that'd be 2, then minus 2, that's 0. And then plus, 5/3. So 5/3 is what I'm getting here. And remember, basis c was simply the number 1, right? The basis for the real number. So 5/3 times 1. Translate that back. This is 5/3. And we can double check this, right? Let's take the integral from 0 to 1 of 2 minus 4x plus 5x cubed, or 5x squared, sorry. This would be 2x minus x squared, or sorry, 2x squared. 2x minus 2x squared plus 5/3 x cubed. And then I plug in 1, and that'll see me 2 minus 2. That'll be nothing. So I'll have 5/3, and then I plug in 0. I get 5/3. It works. So, and you can do this for any linear transformation. You can change it into a little equation involving the coordinates with respect to the bases for the domain and the codomain, right? Where you change your input to its coordinates with respect to the standard basis for the domain, and then your output, right? You can find your output by multiplying that standard matrix by that input coordinate vector, and then that product will give you a coordinate vector where the coordinates are relative to basis c, which is a basis for the codomain. And then you can use those coordinates and that basis, make a linear combination and find what the output should be. All right. Or you can, of course, just plug it into the rule. But this is just to show you how every linear transformation, every single one, is just like the linear transformations between Euclidean spaces. Do you see how it ended up here? I basically went from R3 to R1, right? And that's because our domain had dimension 3, our codomain had dimension 1. So whatever the dimension of the domain is and the dimension of the codomain is, you can actually set up a little rule involving coordinates that is just like setting up a rule between the Euclidean spaces with those same dimensions. All right. Said a lot of fancy words, I know, but I'm hoping that through these several examples here, you're seeing what I'm saying. All right. Okay. I hope you enjoy practicing taking linear transformations and writing them as coordinate representations, coordinate vector representations of them involving the standard matrix. All right, and thank you very much for watching.